back to my limit series. Today, we are going to be going over the limit definition of a derivative. Now, there are probably a lot of different ways to rigorously define what a derivative is, but we're going to start from the intuitive understanding and show how that can lead us to our limit definition. So for now, let's say that the derivative is the slope at a point. And I'm going to write that down because this is going to be the idea that I want to focus on for this video. That we're looking for the slope at a point. And you might be looking at this and thinking, well, you can't really have the slope at a point. If I just draw a point in space, there's no inherent slope. I would have to draw another point in relation. And then there's the slope of a line. And while it's correct that the slope is inherently referring to the context, if you will, of that point, we can think about a function. So perhaps I'll draw a graph of a function. And let's say I'm really curious about the slope of this point right here. And I might ask, can you draw a line that has the same slope as this point? Well, you kind of look at the context of the function and see, well, right around this point, it would kind of make sense for it to have a slope that kind of looks like this line I just drew. Now, of course, what mathematicians have done is taken this kind of idea, and this is called a tangent line, by the way, and turned it into a rigorous mathematical definition using limits. So, to start, let's think about what is a common definition of slope, which you probably see as the change in y divided by the change in x. Right, if you have a linear equation, for example, we could look at this tangent line right here. You could look at any change in y and then look at the corresponding change in x. And that would be the slope of your line. Now, we can also think about slope as the slope between 2 points. So our delta y might be y2 minus y1. And our delta x might be x2 minus x1. So for context, right, we might have a point x1, y1. This is a coordinate. And then we have another coordinate, which is x2, y2. So we take the distance between our y2 and our y1, that's the change in y, and the distance between x2 and x1. Of course, there's way too many variables here. Right now there's 4 variables, so how can we make this more simple? Well, again, we're looking at a function, right? So really, these y values are determined by the function of x. So this is equal to f of x2 minus f of x1. And this is all divided by x2 minus our x1. So let's give sort of a summary of what we have right now. So let's say we have a function, and our function is a function of x. And I'll keep this example for now. we have 2 points. We have x1, and the y-coordinate is f of x1. And we also have an x2, with the y-coordinate being f of x2. And the slope is the line that goes between these 2 points. So I just drew a straight line. I said disregard the rest of the function. Because really, that's all that this slope equation can do, is just take 2 points and find the direct line between them. So how can we get the slope at just 1 point? Well, we can do that by having the 2 points be really, really, really close together, right? If instead I did this secant line with a point right here and a point right here, the slope basically looks the same as the function. And if we made them as close as possible, it would essentially be exactly the same thing. Now we can show what that means mathematically. So instead of just having any 2 arbitrary points, x2 and x1, we're looking at a specific x value and another value that's really close. So instead of x1 and x2, right, we just have an x. So let's have our x1 just be our x, because that's the point we're focusing on. And x2 is really close to x. So it's x plus a small h value. So let's make that substitution. We have our f of x2, which now is f of x plus h. And we're subtracting our f of x1, which x1 is just x. So now we have x2 in the denominator, which is x plus h. And x1 is what we're subtracting, which is equal to x. And you might notice that conveniently, right, this x and this x cancel out. And so we could draw, right, what this looks like on the graph. So we have our x1, which is now just an x. And our x2 used to be all the way over there. But now it's just a small distance h away. So this is x plus h, f of x plus h. And so what we want to look at is what happens when this h gets close to 0 as possible. Or in other words, the limit as h approaches 0. So I'll write that down. We have the limit as h approaches 0 of f of x plus h minus f of x. And this is all divided by h. And to be clear, it can approach 0 from either side. So h can either be really small positive or really small negative. And essentially what this is saying is that it's the distance, right, or it's the slope between 2 points, and h is the distance between those 2 points. And it's saying what is the limit as that distance becomes smaller and smaller and smaller. So essentially we get to the tangent line that we want to get to. And so what's important to note is previously we were looking at a limit of a function. We could graph the function and kind of intuitively see where would this function approach. But of course this isn't really something we can graph, right? Because there's a bunch of different functions if you were to plug in values for h. So this limit here is conveying a different idea. We are no longer graphing a function. but we are thinking of this concept of an infinitesimal distance from there which determines our slope. And this is where we get our limit definition of a derivative. Thank you very much for watching.